So this is the 17th session on rigid body kinematics. So in this also we'll take up some numerical problems on pure rolling. Okay. Now theory of pure rolling has been discussed in great detail in the 16th session. Okay. In session 15. In 15th session the detailed theory of pure rolling was discussed. In 16th session numerical on pure rolling was taken up. In this also I'll take up numerical on pure rolling. Okay. So if you know the theory of pure rolling, then you can directly come to this 17th video on rigid body kinematics. But if you don't know the theory of pure rolling, then you must first go to 15th video on rigid body kinematics. Then you read the theory, then you come to 16th and then you come to 17th. Okay. So I'll take up a numerical problem on this pure rolling in this 17th video on rigid body kinematics. So first I'll write down the problem. Okay. Solid cylinder. A solid cylinder of radius r and center at C rolls without slip over a horizontal surface and its center moves at a rightward speed v. The coordinate system has been shown and is fixed with respect to ground. Also, at time t equal to 0, P naught is the highest point of the drum. Highest point of the drum as shown. Okay. So I will first draw the diagram, okay, and then whatever questions will there I will just mention and then go on solving them one by one, okay. So the diagram of the situation is as shown. This is the drum, side view of the drum. This is the center C of the drum. R is the radius of the drum. This is the fixed horizontal surface. This is the origin O of the coordinate system. Rightward direction is the x-axis. This is the positive y direction. Okay. This is the positive y direction. This is the x direction. This is the center C. This is the drum at time 0. Center C is moving at a constant speed v rightward. And this drum rolls without slip over this fixed surface. Now for pure rolling, since v is rightward, so for pure rolling the rotational sense of rotation should be clockwise. This is omega. This is P naught point. Okay. So this is the overall situation. Okay. This is the situation at time 0. Fine. And P naught is the highest material point of the drum at time 0. P naught is the highest material point of the drum at time 0. Now we have to specify several things we have to calculate. Okay. First thing is this. Find the relation between V omega and R. relationship between V omega and R. Find the relationship between V omega and R. Here pure rolling is taking place. This is a fixed surface, x-axis. Coordinate system is attached to the ground as I stated here just now. Fine, alright. So find the relationship between V omega and R. That is the question. You have to find the relationship between V omega and R. Alright, fine. Now relationship between V omega and R has already been found in the previous video. In the 16th video on rigid body kinematics, okay. So I'll use it directly. If you want, you can go refer to that 16th video. In the beginning itself, the proof has been given. So answer is equal to just V equal to omega R. This is the relation. Okay. This comes from the pure rolling criteria. Okay, fine. Alright. So V is just equal to what? Omega R. V is equal to omega R. Okay. This is the required relation. Well, I'll tell it here itself. Why should I tell you to refer to 16th video? I'll prove it here itself, alright? Also at time t equal to 0, the lowest material point of the drum coincides with origin O of the coordinate system. Okay. Lowest material point of the drum coincides with the origin O of the coordinate system. Alright. So I'll prove it here, okay. I'm just proving it here. So directly what we do, we take the lowest point of the drum to be P dash at time 0. Okay. So now we have to find the relation between V omega and R. Alright. Now the question is how to find the relation between V omega and R. We apply SRC for velocity between C and P dash. So SP arrow C, OP arrow P dash. C is the selected point, P dash is the other point. We draw the line joining SP and OP, that is C and P dash. This is the line. C and P dash, okay. Now give the velocity of selected point C to point P dash. Velocity of C is V rightward, so P dash also I give V rightward. Then P dash moves in a clockwise circle with C as center and radius R. So P dash, for this circular motion, P dash should have a leftward speed of omega R. Velocity of P dash will be resultant of these two. But this point O is fixed in ground. Velocity of this point with respect to ground itself is 0. From pure rolling criteria, velocity of P dash should also be 0. So resultant of these two should be 0. V minus omega R should be 0. So V equal to omega R. This is the required relation. Okay, alright. This I prove it using SRC. Alright. So we can prove this relation in one more way. That is also a very powerful technique without using SRC. See, the basic point is this. For a rigid body undergoing plane motion, angular velocity of rigid body is equal to angular velocity of any of its line in its base plane. In any of its base plane. I mean to say that if I take any line in this base plane, suppose, angular velocity of that line will be just with the angular velocity of the body. Is it clear? Angular velocity of this drum is just equal to angular velocity of any of its line in its base plane. If you take any line, if you take any line fixed in the body and lying in your base plane, then angular velocity of this line is also the angular velocity of the body. Okay? Or we can say that angular velocity of body is also the angular velocity of this line. Alright. Angular velocity of body is also equal to the angular velocity of this line. This we can say. Alright, fine. So you see what I said do now. I take this line CP dash. This line CP dash is fixed in the drum. So angular velocity of this line is also the angular velocity of the body. But angular velocity of body is omega. So angular velocity of this line is also omega. But we know the angular velocity of line in plane motion is what? Relative normal speed by separation. This I have discussed in the previous videos. So velocity of C is how much? V in rightward direction. Because of pure rolling, velocity of P dash is same as velocity of O. But O is fixed in ground. So velocity of O with respect to ground is 0. So velocity of P dash with respect to ground is also 0. So velocity of P dash is also 0. And V is at right angles to line CP dash. Angular velocity of this line is relative normal speed by separation. Relative normal speed will be V minus 0 by separation R, that is omega. V is also equal to R omega. Okay, so one thing has been found. Alright, now I'll rub this one. Now second relation is this. Find the parametric equation of the trajectory of point P naught of the drum with respect to ground. I'll write the question here. Find the parametric equation of trajectory. Find the parametric equation of trajectory of point P naught of the drum. Of point P naught of the drum and draw its shape. And draw its shape. Alright. So we have to find the parametric equation of trajectory of point P naught of the drum, and also we have to draw its approximate shape. Alright. So now what I do, I redraw the diagram here, okay. This is the drum, this is the point P naught, this is C, this is R, this is the origin of the coordinate system, this is x-axis, this is y-axis. Since the rotation of drum is omega clockwise, as I stated just here. This is the drum at time 0. At some time t, drum moves ahead. Point P naught, which was here initially, it has come here. P dash, which was here initially, P dash. This P dash has come here. This is the line joining P naught and P dash. This is the center. This is the initial vertical line. Okay. Now see, suppose the coordinates of point P naught are x, y. Let this angle be theta. This also becomes theta. So we have to find the parametric equation of trajectory of point P naught. Parametric equation of trajectory meaning we have to express its coordinates x and y in some third variable in terms of some other variable. Say third variable, say theta. That will be the parametric equation of point P naught of the drum, which rolls without slip over a fixed surface, and its center moves at a constant speed v. Alright. So now see, first of all, center C is, he was here at time 0, here at time t. Center is moving at a constant speed v. In time 0 to t, center moves a distance vt, speed into time, speed is constant. And this distance is r, so this becomes r sin theta. So x coordinate of point P naught becomes this distance plus this distance. I have dropped a normal from here. X coordinate of point P naught is this distance, which is this distance plus this distance. This distance is how much? Vt. And this distance is same as this distance. This is r, this is theta, this is right angle triangle. So this is r sin theta. Okay, fine. Alright. So now I'll drop this one. Now, V from pure rolling criteria, V is what? V is equal to r omega. So we just replace omega V by r omega here. So x equals to r omega t plus r sin theta. Now, Angular speed of the body is omega. As I stated just now, angular speed of line P naught P dash, which lies in a base plane, that is also omega. But V is equal to R omega. V is constant, omega is also constant. Angular speed of this body is constant. So angular speed of the line P naught P dash is also constant. But angular speed is angle turned through by line in 1 second. So in 1 second, line P naught P dash turns through an angle omega. In t second, it turns through an angle of how much? Omega t. So this theta should be just the rotation angle of this line P naught P dash. So theta is just equal to omega t. So this omega t will be replaced by theta here. So x becomes r sine theta plus r theta plus r sine theta. So this is the parametric equation of this is the x coordinate of point P naught in terms of parameter theta. Now we have to write down the y coordinate of point P naught. Y coordinate, we drop a normal from point P naught on the x axis. This is the y coordinate of point P naught. This is equal to this distance plus this distance. This is r and this is r cos theta. So this distance is r plus r cos theta. So y coordinate becomes r plus r cos theta. So this is the parametric equation of trajectory of point P naught in terms of angle theta as the parameter. This is the parametric equation of trajectory of point P naught with angle theta as the parameter. With angle theta as the parameter, okay. Now you must note from this theory of mathematical theory that this is the parametric equation of cycloid. This is the parametric equation of cycloid. This is the parametric equation of cycloid. So point P naught moves in a cycloidal path with respect to ground. Okay, fine. Now I love this one. Now we have also been asked to draw the approximate shape of trajectory of point P naught. That also we have been asked to draw. So I'll draw the approximate shape of cycloid. It will be something like this. And so on, like this. Initially P naught was here. This distance will be maximum height 2r. This is also 2r. And this distance will be equal to Vt. Distance moved by center in one time period. Vt is nothing but V is r omega. Omega t is 2 pi. This is the cycloidal path of cycloid. This equation is this curve represents a cycloid. This represents a cycloid, okay? So point P naught moves in a cycloidal path. These curves are called the branches of cycloid. They are called the various branches of the cycloid. They are called the branches of the cycloid, okay? This is the approximate shape of trajectory of point P naught. It is a cycloidal path. These are various branches. Alright? Now I love this one. First we have to prove the relation between V, omega and R. Okay. Second, we have to find the draw the approximate shape of trajectory of point P naught. Okay, and name equation that also has been done. Third is this: we have to find the distance covered by point P naught in one full rotation time period. Find the distance S covered by point P naught in one full rotation time period. In one full rotation time period. Find the distance covered by point P naught in one full rotation time period. That is in time t. T is the one time period of one full rotation. Okay, fine. So to solve this third part of question, I'll again draw an approximate. I'll draw the initial diagram again. This is the drum at time 0. This is the coordinate system x-axis. This is the y-axis. This is point P naught at time 0. Okay. This is the origin of the coordinate system. This is the center. This is radius r. Center is moving at a constant speed v. It is rotating at a constant angular speed omega. P naught is the highest point. This is the drum at time 0. At time t, drum has moved ahead. Point P naught has come here, C. This is C, this is P. This angle is theta. Theta is just equal to omega t. Okay. The velocity of P naught, coordinates of P naught are x, y. Alright, fine. Now we have to find the distance covered by point P naught in one full rotation time period. Now let the speed of this point P naught at time t be V naught. Okay. Speed of point P naught at time t. We know that speed is equal to ds by dt. ds by dt is V naught. Alright, fine. So ds by dt is just what? V naught. V naught is equal to ds by dt. Alright. V naught is just equal to what? ds by dt. Alright. So ds equal to V naught dt. ds is the distance covered by point P naught in time dt seconds. So distance covered by us in time one full rotation time period is this. V naught dt 0 to capital T. Alright. Here it will be, here it will be S, not 0, S. Okay. This I'll grab now. Now V naught is the speed of P naught at time t. Now how to find V naught, that is the question. We apply SRC procedure of velocity between C and P naught at time t. C is moving at a velocity V and omega angular speed is omega constant. So SRC between C and P naught at time t. For that the selected point is C, other point is P naught. We draw the line joining SP and OP. We draw the line joining C and P naught. With the velocity, we give the velocity of selected point C to P naught. Velocity of C is V rightward. So we give the velocity of V to P naught rightward. Now we write down the sentence. Omega is clockwise. P naught moves in a clockwise circle with C as center and radius r. So P naught will give us speed of how much? Omega r. Omega is at right angles to line C P naught. Omega r is also from pure length at area, it is V. This angle is theta. By geometry, this angle is also with theta. So Vp naught is the vector sum of these two. Vp naught is V naught. Root under V square plus 2V square cos theta. 2V square into 1 plus cos theta. 1 plus cos theta is 2 cos square theta by 2 from trigonometry. Okay, fine. So this becomes 2V mod cos theta by 2. Modulus because speed is the magnitude of velocity. Okay. And now we know theta is how much? Theta is just equal to omega t. This also we know. Fine. Now you see one thing. our t will vary from 0 to capital T. Alright, small t will vary from 0 to where? Capital T. So omega t will vary from omega t to 0. But omega t is what? 2 pi. Omega t will vary from 0 to 2 pi. Omega t by 2 will vary from 0 to pi. But in 0 to pi, omega t by 2 will vary from 0 to pi. But in 0 to pi, cos will change sign. Alright, fine. Now what I do, I rub this one. Alright. So distance S covered will be integral over V naught dt 0 to t. V naught is this much. To V mod of cos of omega t by 2 dt 0 to capital T. Alright. 0 to capital T. 2V comes outside. Mod of cos of omega t by 2 into dt. Alright, fine. Now we have to integrate this. Now I have seen that omega t by 2 varies from 0 to pi. In 0 to pi, cos changes sign. So what I do, I will break this integral into two parts. Okay. I will replace omega t by theta. So let omega t equal theta, already we know omega t is theta is omega t. So theta is equal to omega t. So d theta is equal to omega dt. Omega is constant. Okay. So now S becomes 2v 0 to where upper limit of lower limit of t is 0. The lower limit of theta is also 0. Upper limit of small t is capital T. So upper limit of theta will be omega t. Mod cos omega t is theta. Theta by 2. dt becomes d theta by omega. Omega is constant. Omega comes outside the integral. 2v by omega 0 to omega t is 2 pi. Alright, fine. Cos theta by 2 d theta. V by omega becomes r. 0 to 2 pi mod cos theta by 2 d theta. Alright. I'll grab this one, okay? Now what I do again, replace theta by 2 with phi say. Let theta by 2 equal to phi say. So theta is equal to 2 phi. D theta is equal to 2 d phi. Now replace here. S becomes 0 to 2r. When the lower limit of theta is 0, lower limit of phi will also be 0. Upper limit of theta is 2 pi, upper limit of phi is 2 pi by 2. Pi. Mod cos theta by 2 becomes how much? Phi. Mod cos phi, and d theta becomes what? 2 d phi. 2 comes outside, so 4r. 0 to pi. Mod cos phi into d phi. Now I break this integral into two parts. 0 to pi by 2. Pi by 2 to pi d phi. Mod cos phi. Alright. Now, in 0 to pi by 2, cos is positive. Cos phi is positive. So, mod cos phi is just cos phi. So, I replace modulus sign here. Cos phi d phi. Pi by 2 to pi, cos phi is negative. So, mod cos phi will be written as minus cos phi. So, this here right here is minus cos phi into d phi. Pi by 2 to pi. Alright. Now this I rub it. Okay. So S becomes 4r integral cos phi d phi 0 to pi by 2. Cos phi d phi 0 to pi by 2 becomes cos phi d phi 0 to pi by 2 minus cos phi d phi pi by 2 to pi. This becomes 4r cos phi when integrated with sin phi. Insert limit sin pi by 2 minus sin 0, that is simply 1. Cos phi का limit integral of cos phi is sin phi minus of sin pi minus sin pi by 2. Sin pi is 0, sin pi by 2 is 1, minus 1 becomes 4r. 1 minus was plus 1 plus 1, that is 4r into 2, 8r. This is therefore the required answer. Alright, fine. So distance covered by point P0 on the circumference of the drum in one full rotation time period is equal to 8r. So this is the result. Okay, fine. So in this 17th session on rigid body kinematics, I took up this problem. Okay, fine. So this I fully demonstrated it. Alright. Now in next video also I will make some more, take up some more questions on these this concept. Okay, fine. This I close it here.